Good afternoon, and thank you for joining us for the 41st webinar in the Offshore Wind series, Learning from the Experts. I'm Layla Lashmawi, a Senior Project Manager on NYSERDA's Offshore Wind team, and it is my pleasure to be joined by today's expert, Brad Winer with Con Edison, on the topic, How Converter Stations and Substations Support Offshore Wind. Before I introduce Brad, a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Expert series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov or fill out a survey also available on our website, nyserda.ny.gov/osw-webinar-series. Please note that the views and opinions expressed in this presentation are those of the presenters. Next slide, please. It is now my pleasure to introduce Brad Winer. Brad is the Director of Transmission Project Development at Con Edison, where he leads the integration of clean energy projects into the power grid. Brad has over 20 years of experience in the energy industry. He has successfully led initiatives to upgrade and modernize grid infrastructure using innovative technologies, stakeholder collaboration, and best practices. Brad utilizes his expertise to serve as a member of the Construction Industry Institute and Project Management Institute. Brad holds a Bachelor of Science degree in Organizational Management from Manhattan College, a Master's of Business Administration from Fordham University, and he is a veteran of the United States Nuclear Navy, where he served as a nuclear reactor operator aboard the USS Enterprise. Thank you so much for joining us, Brad, and I'll pass it over to you now. Thank you so much.
All right, so thank you, Layla. I really do appreciate the kind words and the introduction. And I want to thank NYSERDA and the entire staff for reaching out and providing us the opportunity to have this conversation today. And I also want to thank all of the participants who took the time to register and are spending the hour with us to have a conversation around converter stations, substations, and the integration of offshore wind. So let's go ahead and get started. The next slide, please. So our agenda today is I want to talk a little bit about who Con Edison is, our clean energy commitment. Then we're going to talk about the electric transmission system, both from a general perspective of the state of New York, but then specifically in New York City. We're going to dive into having a conversation around offshore wind injection, which we'll talk briefly starting from the actual offshore wind turbines, working our way all the way into the grid, and talk a little bit about each step of that process. Please note, we're not going to get into a significant amount of technical detail for each of those items, but just those areas that are important to understand how that particular technology and that new generation source, how it's going to support the grid as we move forward. We're going to talk about sometimes an overlooked aspect, which is the final grid connection, so coming from the converter station to the grid itself. And then I'll share a few takeaways that I have, and then hopefully we'll have a robust opportunity for questions and answers. So let's go ahead and jump into it. Next slide, please. So just as a point of review, if for folks that don't know, so Con Edison, we supply gas, electric, and steam to around 10 million people within a relatively small geographic area. In fact, our service territory is represented in the blue on the map, and it represents around 660 square miles. What's interesting about that, that's only about 1% of the total square miles area in New York State. However, we do consume about 44% of the electricity needs. I find that really interesting, because there's so many people that come to New York City, that live in New York City, that work in New York City, and that each and every one of them is going to utilize electricity in their day in and their day out life. And we're going to talk a little bit about that. We also provide natural gas to 1.2 million customers, and we operate the largest steam system, district steam system in the world, where we provide steam to 1,500 of the most iconic buildings in New York City. Think the Empire State Building, the Chrysler Building, Rockefeller Center, really great places. Next slide, please. So what's really interesting about New York and the service that we ultimately provide to our customers is it's super compact in its area. But that does not mean that we don't have a tremendous amount of assets to be able to provide that electricity on a consistent, reliable, and safe manner. In fact, we have enough underground distribution cables to circle the circumference of the Earth 4 times. We also have 760 miles of underground transmission feeders. And this is a really important point to keep in mind as we go through the rest of the conversation this afternoon, because as we go to introduce new clean energy resources, we're going to have to introduce significantly more transmission feeders. Our service territory is supported by 40 transmission substations and 63 area substations, and we're going to talk a little bit about that in the coming slides. One of the items that we want to keep in mind as we go through each and every one of these slides is that it's imperative that as we make this transition to our clean energy future, we do so keeping in mind that we have to maintain the safe and reliability operation of our system. 10 million people depend upon it in a day in, day out, daily lives, from going up and down in their buildings in a vertical city to also being transported to their workplace to their homes and vice versa. So very important that we keep in mind that we have to maintain that reliable system as we integrate offshore wind. Next slide, please. So that point is really defined in this particular chart. You'll notice that on the last 3 columns on the right are Con Edison's performance and reliability. We are one of the most reliable, if not the most reliable system in the United States. Our customers have come accustomed to not having interruptions of their service. That interruption, as I mentioned, could be catastrophic for the folks that live within the city, because imagine if you live on the 40th floor of a skyscraper and the power goes out for a significant period of time. You're going to be impacted by not only your ability to get in and out of that building, but also being able to heat your building, being able to utilize the restroom, being able to move about your daily lives. So although some of us, as I live outside of the city, are used to expect to have a service interruption every now and again, and even though it's a disruption, we'll be able to manage through it fairly well. The folks in the city are specifically susceptible to challenges in that space. So again, we stride ourselves, and everything that we do is done through the lens of ensuring that our products can be provided safely and reliable. So each and every time somebody comes into their home and hits that light switch, power is available for them to utilize their in every way they choose to. Next slide, please. So unabashed plug for NYSERDA strategic plan. For those who haven't had the opportunity to read it, I truly recommend that you do so. But in this plan, we're laying out what our clean energy goals are. And Layla did a great job. This webinar, this discussion is really focusing on injecting 9,000 megawatts of offshore wind into New York, 6,000 New York City, 3,000 in Long Island. But as you can see by this map and within the other points of our goals, this is a multi-pronged effort that's going to require us to look at the way that our energy is developed, delivered, and used. Clearly, as we go through this transition, we need to keep in mind how do we do this? How do we meet these goals while maintaining that safe and reliable operation? That's going to be a theme as we kind of go through. Because of our commitment to that delivery of service, as well as our steadfast support of these statewide goals, as well as the city goals that are listed on the right, we've developed as a company, next slide please, our 5 pillars of our clean energy commitment. Today, we're going to focus on 2 of them. The first is building the grid of the future, because as we inject new clean energy resources, we have to modify the grid. And we're going to talk about that here in a few moments to be able to accept and be able to transmit and be able to utilize that power safely and reliably. The second point that we're going to talk about today is the last on the screen, which is partnering with our stakeholders. These conversations. We want to make sure that we understand and hear from all levels of the stakeholders what their concerns, what their challenges, and what their focus areas are, as well as provide as best we can understanding of what we're doing, why we're doing it, and why it's so important that we work collaboratively as we move forward through this process. Next section, please. So I think it's a very important place for us to start is to talk about the electric transmission system in the highest level possible. If you go to the next slide, let's start by just taking a moment to take a step back and think about how electricity is made, transmitted, and used. So I'm going to use the numbers that are on the slide here for this purpose of the conversation. And as you'll notice in section 1, you have the generating sources. Now, what's interesting is you'll notice we have our traditional carbon-based generators that are bottom left next to the solar field. We have our hydro, our nuclear, and our offshore wind. For the purposes of a generation system, most of the power, the exception of the solar, comes from having a piece of equipment that's rotating. And that's going to run through a generator, and that's going to generate our typical alternating current electricity. That electricity and that process is no different with the offshore wind. It's just the manner in which it gets transmitted. And we're going to talk about that in the later section. But if you go from number 1, so when the electricity is generated, you have to go and you have to step up under a traditional AC system through a set of transformers, typically at a substation, to be able to get it to a voltage that we can transmit it long distance or transport it long distances. The vast majority, and you'll see this in the slide in a minute, of the power in New York is generated upstate and to the west. So we need to be able to raise that voltage so we can be able to move it across the system to account for the losses and the other electrical concerns before we can get it to a place where we can use it by the customer or the load centers, as we like to call them. Number 3 is the transmission system itself. Now, this is a little bit deceiving because everyone thinks transmission systems and they think the overhead towers. And I think as all of us know, that's not the only items that are in that system. We'll talk a little bit more about that in a little bit. But this is your transmission towers, your conductors, your switching stations, and all of your other power equipment that's used and installed, at intervals along the way to continue to boost and address the power during light load and in high load conditions. It gets closer to the city centers. It goes to an area transmission and area substations in 4, in which it takes it from the really high voltages down to a more usable voltage, and then brings it down again to our distribution voltages, and then gets over to our customers in box number 6. And that will be a varying of 120, 208, 240, depending on the circumstances of the individual customer. If we go to the next slide, I want to introduce you to a diagram that we use quite frequently within Con Edison to try to explain our system. So all of those generation points that we saw just a few minutes ago are still showed on the left side. It's demonstrated by the powerhouse with the stacks, and then it goes into the transformer, and then the transmission substation and area substation. What you'll notice, though, as I want to bring your attention to, is there's a couple of things that are unique to our system, which is the network alignment for the distribution, which is in the middle of the page itself. So whereas most folks are typical of seeing radial connection, utility poles going down the street, cable run, and then taps for with little transformers going to homes. In New York City and other dense populated areas, you have a network system. It's one of the reasons why we have, that a tremendous amount of distribution cables that are within the streets themselves. I also want to point out that there's connections to other grids that goes up to the transmission system. So a little bit different than the map the diagram I just went through, but really think it's important. As we go forward, we're going to be focusing predominantly from the transmission substation, little blue box in the center, to the left, over to the actual generating source and the transformer. We're not going to talk too much about the distribution system, although phenomenally important that we keep in mind, because at the end of the day, we have to move that power in the most efficient and cost-effective manner to the customers. Next slide, please. So let's take a moment and think about the way that New York State's transmission system was built generally. You'll notice by the way the boxes are kind of laid out, this is intended to look like New York State. And what you'll notice is that in a more, or I should say a less urban or dense environment, we typically use switching stations, from the point of generation all the way down into our load centers. And then we'll tap off those switching stations. And I have a diagram in a couple minutes, I'll get into that in a second, into our substations that get down into load. So there's a situation where the power is transferring from the west to the center, from the north to the south, and then ultimately going down to New York City and Long Island in this situation. Included in the switching stations are other pieces of equipment necessary for transmitting AC long distances, let that be capacitors, shunt reactors, and the like. If you go to the next slide, I want to show you what it looks like in New York City. So on the far left of that diagram, you'll see the switching stations themselves. So it's picking up from that map that we just talked about, and it brings it into this 345, 138 system in which we utilize substations to be able to provide injection of additional generation. Those are your peaker plants or your base load units that are located within New York City, as well as load centers. Now, the reason why we do this is because the reality is in New York City, it's 660 square miles. You do not have a tremendous amount of real estate to be able to put large-scale switching stations, then a large-scale transmission substation, then a large-scale area substation without having significant disruption. So we utilize both the 345 and the 138 system to be able to supply load most efficiently. So our higher load customers, say Amtrak, MTA, they may get a 345 tap, where customers and buildings may be at the 138 and then further down from the area station. Just for those that may be asking, the little triangles are loads and the little circles are generating units. And what's interesting is that over time, we're going to be looking to move away from and remove and replace those little circles for the in-city generation with clean energy resources, predominantly for downstate offshore wind. So the question becomes, how do we then make the connection, into the existing grid while introducing offshore wind? The next slide is just going to give you a visual representation of what diagrammatically of what the difference between the switching station and the transmission station. So if we go to the next slide, please. So on the left is your switching station. So it's, as compared to what's on the right, which is the transmission station. A lot of the equipment is the same: bus, breakers, individual connections for leads, either from transmission or generation. What you'll notice, though, is on the right side, our transmission substations, have a combination. They're slightly bigger. They provide the opportunity, a combination of serving local load as well as injecting transmission, and ultimately serving the function of both that switching station as well as a load area. So as we continue the conversation, as we look at offshore wind and we look at the components that we're going to use to bring that power into New York City, it's from our perspective that we'd like to see that we utilize the space available in the most cost-efficient manner, and that's the combination of a transmission substation, and not what perhaps some folks have seen in other parts of the country, which is going to bring in a switching station. So just something to keep in mind as we go forward. Next slide, please. So now now that we've talked about the grid a little bit, let's talk about offshore wind. So on the next slide, you'll remember this is our diagram that we talked about a few moments ago. And on the left-hand side, we've taken out that smokestack generating station, and we replaced it with offshore wind and the converter stations. You'll notice that there are 2 converter stations, and we have a couple diagrams that show where this is in relationship to water and land as we go through this conversation. But the reason I wanted to show this is at the end of the day, the system that is currently there today will be the system that is there tomorrow to ultimately serve our customers. The only major difference is that we're going to use different technology, and we're going to use different components to be able to make those connections. So if we go to the next slide, please. I do want to take a moment and just talk about the general or the most common HVDC configurations, starting with the first 2. Bipole and symmetric monopole, or monopole for the purpose of this conversation, are the most widely used or the most expected to be used within North America. They're very similar in their operation and their construction, except for 2 major things. One, the bipole is bigger. It needs about twice as much land, and it provides greater delivery of power. It also provides a couple of reliability opportunity as compared to the monopole. Monopole, however, is the system that we typically are seeing being deployed for the purposes of connecting offshore wind. That will clearly change over time as technology, cost, and the like goes down. But for the point of this conversation, we're going to be talking about monopole. Back-to-back is typically used in systems that are connecting, 2 different systems themselves. So perhaps there's a frequency issue or 2 different operators. They're typically combined. We're not going to talk too much about back-to-back. And multi-terminal is got an incredible opportunity for us as this technology continues to grow to provide us with the ability to start building out broader and more robust networks. This is still in the relatively early stages. Some folks are definitely looking into that, but it's more specific to some opportunities over in Europe, and it will eventually come here to the United States and North America. So we go to the next slide, please. So let's take a moment to just talk about offshore wind relatively simply. So this is just a diagram that demonstrates the major components. So starting on the far left, you have the generators themselves. This is the offshore wind individual generators, and they are connected in an intra-array manner. Individual power that's produced by catching the wind, spinning the turbine, running through a generator. So very similar to a combustion driven generation, except instead of burning fuel, we're using offshore wind. That AC power is connected onto your offshore platform. It's going to be converted. We're going to talk about that in a second, over to DC to be able to be moved long distances across, in this case, the water into the city centers, where it's going to go to a matching converter station, which is going to do the inverse. It's going to flip it from your HVDC down to your AC, and then it's going to connect into the AC grid. So those are the major components. We're going to focus on the converter stations and then ultimately the connection to the grid. Next slide, please. So this is just another diagram that kind of demonstrates, but I do want to talk about it. For those that can get confused with this diagram, starting from the connections over into the 2 overlapping circles into the first box, those are the combination of your transformers and your converters. Those are one particular station. They are connected then between, in this case, is a monopole. So 2 connections that go between the one on the left and the right, and then go back to the grid. The transformer's job is to raise the power to a point to the operating of the converter station. The converter station is then to change it from AC to DC, and then ultimately transmit that across the long distances. Match it, convert it, and then drop it back down to the use level to the existing grid itself. One of the things that I do want to note is that some of this equipment is offshore and some of this equipment is onshore. So we're going to talk about, as we move forward, what is it that folks are going to see when they start experiencing the offshore wind transition as we start to bring in that offshore power. So let's go to the next slide, please. For the vast majority of us, the only thing that we're going to see that is new and different from what's in the existing electric power system is the addition of this beautiful building on the right, or the converter station. For the most part, as I mentioned, the substation itself is going to be there. So depending on if you live in New York City or other major metropolitan where your substations may be housed in buildings, they may be open air. Those substations, there'll be more of them and they'll be a little larger. But the one addition, that we haven't seen a lot is the converter station itself. These are very large buildings. The picture on the right here is actually from our friends from TDI for the Champlain Hudson Project Express. This converter station is actually located in the Astoria Energy Complex in Astoria, Queens. And this is actively being built today. I was actually on site with them yesterday, and it's just amazing to look up and see 5 or 6 stories of a building that's going to house all of the individual components necessary for that HVDC conversion. One of the things that we have to note is these are really large structures. They sit on about 4 to 5 acres themselves. As you'll notice in this diagram, there's certain setbacks to make sure that we meet the individual city codes, the fire codes, and the such. There's multiple components that are in this converter station, but I think the most important thing that we have to remember is for each one of these connections, so let's say using a monopole design for 1,200 to 1,300 megawatts of injection, we're going to need one of these buildings. And one of these buildings are going to be installed hopefully as close to the existing electric grid as possible, or in the case of the LIPA PPTN and the New York City PPTN, in a place where close enough for them to make the injections without adding long lengths of AC cable. And we're going to talk about that here in a moment. But it's important for all of us to know that we're all going to be experiencing the disruption when we start installing the HVDC cables as we go and transition from the sea to the land, as well as the AC cables that go from the converter stations to the substations. But at the end of the day, the one thing that we're going to be left with, if you will, that we're going to be able to see and experience are these converter stations. In a densely populated area like New York City, putting a building size is really critical because perhaps the spaces that are available are a little bit further away from those existing substations or the existing grid itself, right? So 345 in New York predominantly runs on the west part of Queens and through Manhattan. Well, if you take a look at those particular areas, there's not a lot of space for structures of this size, especially when you think through the fact that you're going to need 7 or 8 of them potentially to be able to meet our goals. A couple of other items on the converter stations. Both the schedule and the cost are clearly based on market conditions. $600 million today for this converter station may be $1 billion tomorrow. It may be $500 million tomorrow, depending on the need. But as the industry moves forward and transitions to introducing more offshore wind, the cost of this equipment is most likely going to go up. As equally important, from the moment of setting a contract with an OEM, Hitachi, Siemens, for example, to the point of getting it delivered and installed, it's about a 4 to 7 year period. So Leila talked about, that we have a goal of getting 9,000 by 2035, and then ultimately energy 100% by 2040 from an emissions perspective. It's 2024. That's not a lot of time, and coordination between each and every one of the projects we need is going to be critical to make sure that we can be able to meet our goals. So the next thing that I want to talk to you folks about, and if we go to the next slide, is going to actually be the final connection to the grid. I think, this is one of those parts. We spend a tremendous amount of time talking about the impact of laying HVDC cables within the waterways of New York, and we should. There are significant constraints that we all have to take in consideration as we go through this process. However, we need to make certain that we're also equally concerned with the ultimate connections associated with the AC cables. So if we go to the next slide, I just want to take a couple of moments and point out that for the vast majority of the 523,000 circuit miles of transmission feeders within the United States, the vast majority are overhead. Now, there's a challenge when it comes to overhead because you have to cut out of right of way. You've got to install big towers. You have to install cables. But there are a couple of benefits, as compared to undergrounding those circuits that we have to take in consideration as we have this conversation. The first is typically overhead connections provide for more transfer capability. So if you look and you compare this to our 345 system, you get about, let's for the purpose of this conversation, 1,200 megawatts of transfer versus underground, which will be about 700 megawatts. And the challenge with that is that 700 megawatts is going to change. It's going to be impacted by the environmental conditions, which means that you're going to ultimately have to have more circuits to be able to transmit the same amount of power. So in this example, 2 345 kV circuits to be able to transmit the output of that converter station and to get it into the electric grid. Hence this really important perspective of trying to get those converter stations as close as possible, therefore to minimize the overall cost and the disruption to the community as we make that transition. As such, the cables themselves, undergrounding the cables are more expensive. That's a really important consideration as we continue to determine how does the best way, what is the most cost-effective way to bring offshore wind into our service centers. If we go to the next slide, I want to explain why we have such challenges with installing underground. I love this picture on the left. It's a little bit old, but I think some of you may have seen this previously. This was down in the lower part of Manhattan many years ago, and it kind of gives a depiction of what some of the streets in New York City look like. They're streets that have tremendous amount of existing infrastructure, notwithstanding our electric transmission, distribution, gas and steam systems. There's also telecommunication, sewer, water, just a lot of stuff. Now, I would be remiss to say that every street in New York looks like this because it does not. But when you're installing XLPE or a solid dielectric system within the general right-of-ways, the roads in which people are going to be traveling on, it's really important to consider how much space one needs. If you look at the drawing over on the right, it gives you an example of what a electric circuit installation will look like. You've got your conduits that are wrapped in concrete for its own protection. And then you have a separation between the top of the street, so call that about 3 feet. And then it's not shown here. It's protected by a layer of thermal sand for some reasons we'll get into here in a moment. The thing that we have to note is this is just the duct bank. So you're going to need for each one of these circuits, bigger if you go with a double circuit, but for the purpose of conversation, we'll go with a single. You're going to need a 4-foot by 6-foot structured concrete box, rectangle, that you're going to need to install from a point to a point, from that converter station to that substation. And what's really interesting about this is, these feeders are not capable of just being moved very, very quickly, sharp turns. There's a term in the industry that the bend radius, so you can physically get the cable in and out of the circuit. It's limited. So as you're going through and you're laying out the positions of where this cable is going to be, you have to take in consideration that physical space. And then trying to understand and minimize whatever impacts to the existing systems, either via relocation or by an electrical impact or a gas impact. We'll talk about that here in a second as we go through. But if you could just imagine trying to put a 6 by 6 by 4 box in the middle of a street and putting in 9, 10, 12 of these at a given clip, it's completely difficult to comprehend, or it's not difficult to comprehend the challenges that that's going to possess. There are additional challenges with this that we have to be considerate of. If we go to the next slide, one of the items that, as you're designing a below grade circuit, that we have to be very aware of is that this particular technology is going to have an impact on, it's going to be impacted and it's going to have an impact on existing utilities. And the more circuits that we place in service for the purposes of supporting this, the more impact they're going to have. What you see on the right side here is just a modeling software that we use to try to make certain that we're taking into full consideration what the environmental impacts will be or could be on a particular circuit. When you're working with solid dielectric cable, you want to make sure that you're taking into consideration the heat that it's going to need, the heat that it needs to dissipate, and the impact that it's going to have on those other commodities, those other assets, as well as vice versa. So I mentioned earlier that we use 700 megawatts for the purpose of conversation in order to run that transmission feeder. Well, what you'll find when you start doing your thermal ampacity calculations and other studies is that the environmental conditions, the ability, that space that we are looking for to be able to put that big rectangle of concrete and cable in the ground has resulted in maybe 600, 650, 632, perhaps even something less, which then is going to result potentially in a reduction of what our transfer capabilities coming out of that particular converter station, or having to run an additional feeder. So now we're adding, for how many assets are going to be installed, more costly, more impactful to the overall system. The good thing about underground circuits is, for the most part, they're installed in the ground. So there's not going to present a hazard necessarily to the overall general public. But we do need to keep in mind that we have to access those particular assets as we go forward. And which leads to maybe one of the more challenging concerns as we go through, which is finding a place for a 20 by 30 by 10 manhole. Oh, excuse me, I muted myself. If we go to the next slide, I want to show you an example of that on the right-hand side. So this is an example of a manhole for a transmission feeder that was installed a couple of years ago. This is about 10 foot wide, 20 foot long, and about 10 foot deep. Is installed about 13 foot total impact to the below surface. So as I mentioned before, we go back to that picture a couple of slides ago, finding space for an individual manhole per feeder is just amazing. It's an extreme difficulty. And as we go through this, this is one of the restrictions that we have to keep in mind, is that we're not going to put multiple feeders in a single manhole because we're not going to be able to maintain that properly. So for every system, every circuit we install, we need to install a manhole for it. So if I'm running multiple circuits because I can't get the transfer capabilities because of the environmental impacts, because of the space restrictions, I'm going to ultimately have to find this much space for each and every one of those additional feeders. So if we take back and just do some simple math, if we're looking to get 9,000 megawatts of offshore wind, we may need to run 14 feeders, 14 345 feeders. We're going to need to space manholes every 14 to 2,000 feet, depending on the geographical constraints. And each and every time we install a new one of these feeders, depending on where they are located, they could have an impact to an existing or previously installed feeder. So clearly a very, very critically important step that as we go through and we have these conversations, we need to be planning collectively. I mentioned on the onsite, we did an incredible coordinated planning study for the offshore wind in the water. Fantastically written paper. I do suggest to anybody who had the chance to review it. And it really talks about coordinated effort. I'd extend to folks that as you get into the areas where this offshore wind is going to be injected, which is going to predominantly be Brooklyn, Queens, perhaps Staten Island, perhaps a little bit in Manhattan, there's going to only be a limited amount of landing locations and a limited amount of streets that we're going to have the space necessary to be able to install the overall infrastructure necessary to be able to make that final connection between the converter stations and the grid itself. The last item that I wanted to touch on is the upgrades to the actual substations, the existing grid itself. So I mentioned earlier that reliability and safety paramount in everything that we do. And we're not going to be able to sustain removing pieces of equipment for long periods of time, or retiring pieces of equipment without a suitable replacement. So every one of these is going to require, every one of the connections of offshore wind are going to require us to modify or build out new transmission substations, so we can make sure that we make those final connections to the grid itself. Those connections, those modifications to the existing substations or new substations are going to be project dependent, and they become additive as we go through the transition. And what I mean by that is the upgrades needed for one 1,300 megawatt injection of offshore wind, to the electric transmission system, may be relatively small. Maybe it's a breaker position, maybe it's a relay upgrade, maybe it's a piece of ancillary equipment that needs to get updated. When we start adding the amount of power that we are going to add, those upgrades increase and they grow upon one another. So the impacts on one injection as compared to the rest of the system onto another injection as compared to that system to another results in additional upgrades, right? You may have heard the term bottling, and what that really refers to is when you have a circumstance where the existing infrastructure, the existing feeders are at its capacity, and if you add additional transfer or you want to move power around more effectively, you might have to add additional transmission feeders. So not only do we have the HVDC cables that are coming in to the converter stations and those 4 to 5 acres worth of work, and then we have the 2 or 3 circuits from each converter station getting over to the grid itself. Now we have the updates of the grid itself, but now we may have an impact on the existing transmission circuits where we may have to add another feeder to be able to make that deliverable. So really critical that we coordinate and we understand as best we can, because the first person in is going to have a slightly different challenge than the last person in. And clearly we have a goal for us to hit the electrification. So I'm going to go to the last section of our conversation here today, and which will be kind of the takeaways from my perspective as we go forward. So next slide, please. So one more slide, thank you. So we kind of talked about it. Generation from offshore wind, not all that different than generation from a natural gas plant, from a hydro plant, from a nuclear plant. The technology that's being used, the components that are being used are slightly different, but at the end of the day, we need to make sure that that equipment is connected in such a manner that ensures the reliability and the safe delivery of that commodity to all of our customers. I spent over 20 years of my life working and living within this region and the city, and I'm in awe of the city itself. The vibrancy, the technology, the commercial hubs, the people. But there's one thing that we always have to keep in mind is that without electricity in New York City or other major metropolitan areas, those cities do not thrive in the manner in which they were intended to. As we go and we transition, from not only our utility sector, but also transportation and heating, of our homes, the dependency on this electricity is going to just become greater and greater and greater. So it's incumbent upon us that as we look to power vertical cities, as we look to power all that we do within our economies, that we have to ensure that this power is going to be delivered reliably and safely. We have to consider each step in each component, not from the lens of ourselves individuals, so the offshore wind developer or the transmission developer or the incumbent utility or the customer. We have to look at this in a very collaborative perspective, because the reality is the impacts of building this and establishing this new industry is going to be felt. The impacts is going to be felt by all of us. So as we continue to transition into clean energy, we need to look towards collaboration, to communication, and leverage what each of us bring to the table, the experts in the offshore wind community, in the incumbent utility community, and in the community in general. So I think it's an important point as we go through, because if not, if we go and say, well, I'm going to worry about my part and you're going to worry about your part, two things are inevitably going to happen. The first is we're probably not going to make our goals on time because we're going to put ourselves in a box where we are going to have to potentially undo or add to for things that we could have otherwise we could have avoided. Secondly, it's going to be more expensive. As we go through, and as I mentioned, every time we add a new asset, the more expensive it will ultimately become. So I look forward to the next portion of our program, which is the Q&A, and I really look forward to working with each and every one of you as we transition to bring more offshore wind into New York City, into New York State, into the country as a whole. Thank you so much for the time and opportunity, and hopefully I can answer some questions.
All right, thanks. Thank you so much, Brad, and especially for your closing comments. Could not agree more. We all have to work row in one direction. We're all on the ship together. So, all right, we have a handful of questions that have already come in, and I'm sure more will continue to come in over the next 15 minutes or so. So I'll just get started. There's a question: will these substations require significant redesign for use in the Gulf of Maine for floating offshore wind farms? I don't know if you can speak to floating offshore wind farms, but those.
Yeah, I can't. It's not an item that falls into to my area of speciality. I think that, you know, if you're thinking about it from the grid connection itself, I'd say yes. I think that, you know, as you collect the power and you transmit it locally to the onshore substations, depending on how that substation was originally built, if it was a switching station, if it was a substation, it was just a collecting station, modifications may be required and they may be significant. The good news is most of the system operators have robust plans to study what is required there, as well as the developers' innate understanding of it. So I would expect, yes, they will have to do some upgrades, but it really just depends on the specific application and the specific station that's in question.
Right. Thanks. Our next one is about the footprint for HVDC converter stations. Slide 23 mentions that the site requirement for the HVDC converter station is 4 to 5 acres. Does that include construction footprint and the site control, or just the converter station?
Great question, whoever answered that. So 4 to 5 acres is the approximate footprint that you're going to need for all the equipment necessary to build the converter station. Clearly, this individual has got some experience in construction. You're going to need additional laydown to be able to facilitate the actual execution of the work. There are certain ways that you can stay within a 4 to 5 acre site and build out the work. But I would imagine most developers, if I were building this, I would look to try to have something that's a little bit bigger. That means maybe an adjacent property or a laydown yard close to. But at the end of the day, a good rule of thumb is, if not to say that you can't, all my friends on the call will say, hey, I can do it in 3.5 acres. Not to say that you can't do it in a smaller footprint, but traditionally you want to stay within that to be able to appropriately install all of your equipment. You know, we didn't talk about it, but your converter halls, your admin buildings, your AC yards, as well as providing the appropriate separation for your local ordinance, let that be for fire department, city code, and the such.
Great, thanks. I'm just moving down the list, and there's a question here. The substation that has been suggested for Empire Wind 2 in Island Park, is that a converter station where the electricity would change from DC to AC? I can weigh in briefly, and if you want to pepper on, you're welcome to.
Sure.
Just to clarify, this project is proposing to bring power with HVAC, so it is not a converter station that will be sited there. And also that more information about this project is available on the Empire website, documents about their Article 7 and such.
Yeah, and I would just add that, as we talked about briefly earlier about the existing HD system, when you move power utilizing high voltage AC, you are subject to certain losses and you're subject to certain electrical phenomenon. And so they're all going to have a substation, some type of station that's going to come and address those challenges. It won't be an HVDC converter as we're talking about here, but there will be substation equipment that will be addressed, and it will have a slightly different footprint. I think, as Layla said, I'd check out the website or Empire's literature on that.
All right. How much noise do converter stations make?
Yeah, so I think with all power electronics, you're going to have a certain level of noise, regardless of what you use. When the developers and the engineers are designing that, they're going to try to take that into consideration as they're building that big building that we saw, and to appropriately separate that environment where where some of the noise is emanating and the external environment, to be able to minimize the impact of the surrounding community. It's difficult to tell you exactly what the decibel rating is because, again, if I'm standing right next to the building, it might be slightly louder. If I'm across the block and if it's appropriately designed, you may not have an impact. I definitely follow up with the individual projects that you may be looking at because they'll have some information on that. It is something that's studied. It is something that is designed for it to minimize the impact.
All right. And a clarification, there will be a requirement for 14 new 345 circuits to support the generation.
Yeah, so it all has to do with, so this is what I was saying about the manner in which the transfer is occurring, right? So if you take our theoretical where you can get upwards of 700 megawatts in a particular circuit. So if I've got, that means that I need 2 for every 1,300 megawatts required, right? So if we do the math, depending on what the environmental conditions are, you might be able to get away with 8 or 10 of those feeders, but most likely, especially with what we're seeing, you're going to have to add additional feeders. The point that I was trying to make is it is not a 1-for-1, right? So as we continue to put additional feeders into the ground, you're going to have additional need for that transfer, and it becomes a bit of a math game, right? So if I want to get 1,300 megawatts and I can only get 600 megawatts per feeder, well, I'm either going to get 1,200 megawatts or I'm going to put a third one in, right? And there's an economic, question there. So.
All right. Will there, maybe you can help direct folks. There's a question here about if there's an available list of required upgrades and where in the Con Ed system that they're available for review. So, for example, is there a list of current infrastructure that's shown and then the list of upgrades or an upgrade concept of new anticipated infrastructure, and where can folks reference that type of information?
Yeah, so I would love to have a list of, hey, all of the upgrades that we would need for all of the work. But the reality is, as I was mentioning, there are very specific studies, that are conducted as part of the New York ISO process for interconnection. And depending on what is being suggested or put forth for consideration will determine the amount of upgrades that are required. So let's say, for argument's sake, that you go to a station that does have capacity. We don't have a lot of those, just for the record. And maybe there's a minimal amount of upgrades that will be identified in the studies. If you're going to add, say, 3,000 megawatts into a station that doesn't have capacity, the upgrades of that will be greater. And so there's not a standard list that we can say, hey, if you want to go here, do these 5 things. It is individual project, individual study based.
All right. A lot of comments are complimenting your presentation. So great presentation. And folks are curious if you've seen any change in demand for certain skill sets or knowledge areas, even among Con Ed's teams, as new renewables are coming into play.
Across the board. In almost every aspect of our business, we're seeing an additional need. I always joke, I started my career as an operator, and then I quickly moved to building stuff because who doesn't like building stuff? But for a period of time there, we were building at what was required. So there wasn't a huge area of emphasis. I think today there's the skill sets that, that I'd recommend that people look at is engineering is in really high demand. Power engineering especially is in high demand. So people that can work through and give us the solutions to these challenges. And then you're ultimately going to need all the tradesmen and women that can actually execute and build these work. So, construction individuals across the board, engineers across the board, folks that, like yourself and others, Layla, that, kind of help us educate ourselves about what this is are up. So I think the areas that I look for right now for hiring are obviously experienced power engineers and experienced constructors, especially in an urban environment.
All right. How are you planning for increased demand on the customer side? We know with
Yes.
our transition that the
Yep.
grid is needing to, almost double in size.
Thank you so much for whoever asked that question. I did skip over one of my talking points. So as we go through this transition into electrifying, what we're going to see is we're going to go from a summer peaking electric system of around 13,000 megawatts ish to a winter peaking of more, 20, 25, 30,000, depending upon how electrification comes across. We are looking at this in a very holistic way. One, making sure that we work with all the fine folks that are involved in this process to make sure that supply is available, right? Because we need to make sure, first and foremost, that we can get the energy. Edison doesn't produce electricity. We're a transmission and distribution company, if you will. We purchase that through the markets, and then we transmit it and distribute it to the customer. So the second half of that, and I think what the question is, how are we planning for the customer side? We have a robust planning process that looks at where we have the anticipated load growth over the next coming years. And we look to build out those area substations, which will connect into the transmission, and then build out our networks accordingly to be ready, prepared for serving that particular need. Now, the time and how quick we get there will obviously depend on the adoption rate. New York State has got it figured out, if I may say so myself, so shout out to NYSERDA and to all of the other regulatory bodies. We've canonized these requirements in law. So this is going to happen, right? Whereas other places it's hey, it would be really nice if. Well, when you're talking about building and expanding a system with it, it's a really but if folks aren't going to want to spend the money. Clearly, we know this is a requirement, so we build the transmission with you folks, we build the distribution, understand what loads growth, and we do that all within the next 25 years. One note, just anecdotally on that, is I always like to tell folks, Edison's been around since 1823. We started as a gas lighting company, whale oil, and we go in light gases, and we've seen the transition in the last 201 years to the point we are here today. Our transmission system took about 134 years to build it as it is today. And we collectively get to change that in the next 20 years. So no stress or problems for anybody, but we have quite a bit of work to get it done in a very short period of time.
Definitely. So that segues well into the next question. With the 4 to 7 year planning and execution periods, is the current supply chain able to supply equipment needed in time to meet the current goals?
It's a challenge. I think that most of us who are involved in this look at that as being one of the best, one of the biggest risks that we have. I believe that we are continuing to engage with our OEM and our manufacturers, as well as our other partners within the supply chain, to be able to plan for and build up existing capacities in order to support. I think there is some nuances because we're building a new business model, if you will. So the question is, do I build a plant now for a future need? Do I wait for the need? I think that's a lot of moving parts associated with that. I think closer coordination with all the parties will be able to have an impact to us to positively meet our goals. But it's absolutely a concern that we have to keep in front of.
All right. I'm getting carried away and just realized that we're up against in our last minute, so we only have time for one more question. What types of technologies should be added as part of any grid upgrade? What can folks expect to see everywhere?
Yeah, I'm going to stay with it. reliable technology. I think that when you're talking about the electric grid, this isn't a place where we can take the risk of having something that hasn't been proven, or the first of. That being said, I think that it's all of us would look at this and say that the intermittency of offshore wind has to be balanced by other energy sources and supplemented by batteries, right? So long-term storage that can be able to take and utilize that energy, that when it's abundant, we can use it. The challenge right now is batteries are relatively in its early inception phase. They're doing great, but they need to get to a position, get to a level that we're not looking at an 8-hour discharge period. We're talking about a day's discharge period, and that's going to come in time as the technology advances. I think that focus, and there are a lot of great and smart people that are working on that, is going to really allow us to leverage the full opportunity that renewable energy provides to us.
All right, thanks. Thank you so much, Brad. A really amazing webinar, and thank you everyone for joining us for this Learning from the Experts webinar. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next planned webinars are coming up in May. On May 16th, our experts from Delft University and Tufts University will discuss bringing research into market. And on May 29th, our experts from the National Offshore Wind Research and Development Consortium will be discussing innovations and emerging technologies. You can register for future webinars through our events page at wind.ny.gov. And as always, if you have requests for future topics you'd like to hear about, please email us at offshorewind@nyserda.ny.gov. Thank you again for joining us today, and we will see you next time.